Understanding how light is produced actually gives us a lot of insight to how electrons behave inside atoms. So here's the simulation we're going to look at. This is linked on the website in case you would like to go play with it, but you're going to have a computer. iPads won't work. And like mobile devices aren't going to either.
What if you have Puffin? Yeah, Puffin.
Oh, okay.
I love Puffin.
So, here's the way this is set up. This is much like the tubes that we were using yesterday, okay? Except, just to start out with, we've only got one atom inside there. So what we can do is we can turn on the electricity up here. They've got a battery, but
Battery acid. How many volts is it?
actually, oh, here we go. Okay, so we fire an electron. When the electron hits the atom, it knocks the electron inside the atom. So there's two electrons here. One that gets fired across. Okay, it'll knock the electron inside the atom to a higher energy level. And then when that electron falls back down to the lower energy level, light is given off. Okay, now there's two different ways that is shown. Here, the one tells us that the electron is in the first energy level. And then over here, they've got this chart, and you can see the electron is right here. Okay? This shows us how much energy we are delivering by, hooking up the electricity. So the energy here is enough to actually shoot it up to that second energy level, and we can see that. And I'll fire a few here, and we're going to run them in slow motion so we can see what happens. The squiggles that you'll see show the electron as it jumps from one energy level to the next. So let's fire another electron. For some reason, a little laggy. Holy crap! See, that's much more slow motion than it was. So, see, it jumps to the next energy level. You can see the electron is now up here. And then it jumps back down, and this is the light coming out. Okay? Now, if we look, this is kind of a purplish light because it's high energy. There's a big gap between here and here. I'm going to take it off of slow motion because that was a little too slow. Okay? Yeah, we'll send up continuous again. So here's another one. We'll fire another one right behind it. Okay? And we'll set up continuous here.
How come the light's following that one?
I don't know. That's just the light comes out randomly. Yep. Light's completely random.
So as it's going back out, it's going down energy level.
As what's going back out?
So it hits it, and it goes to 2, and then it comes back out. And as it's coming out...
Okay. The going back to 2 doesn't have anything to do with this electron. Okay? Once this electron jumps this to a higher energy level, it's done. It randomly just like if you took a basketball and you threw it up to, halfway up a set of stairs, it's not going to stay there. The same thing with electrons. When they get bumped to higher energy levels, they just come back down.
Well, yeah, I know, that's what I'm saying. It's climbing as it's getting to the 1. And once it leaves that, it's going back down.
No. Again, there's all these electrons here do is bump the electron that's inside the atom to a higher energy level. So there's an electron here that you don't see, and we're showing the change in energy levels from first to second and back just by the numbers. Okay? Now that electron is shown over here. So this is the electron. Now it's in the ground state. Now it's at the second energy level. It's jumping back and forth. Now the other thing that you can do here is we can set up a spectrometer that will measure the actual wavelength of the light that's given off. It just does. Okay? And what we see here is that there's only one type of light that's given off, because right now the energy that we're putting in is only enough so that it bumps it to this energy level and it gives off one type of light as it falls back down. Allie. It's a good place to pay attention.
I was talking.
Okay. All right. My mistake. It was Gentry. Gentry. It's now's a good time to pay attention. So we can see there's only one type of light that's produced here. But if we change the amount of energy that goes in by changing the voltage here so that it gets to another energy level, yeah, there we go. Now we see red light that comes out because this electron is going to jump up to this energy level, and then it can either fall all the way back down or it can fall to 2 and then back to 1. And there's going to be different types of light given off for each of those jumps. Now right here, the 2 to 1 jump is still going to give off the same type of purplish light, okay? But the 3 to 2 jump is going to give off a lower energy light, that's the red that comes out. And sometimes the electron is going to fall all the way from 3 to 1. It's not going to stop at 2. Okay, so if it falls all the way from 3 to 1, that's a higher energy, and that is what is happening over here. So there is a light wave, we can see right here, it's measuring light that's a little bit higher in frequency, a little bit shorter in wavelength than what we were producing right here.
What causes it to stop at 2?
It's completely random.
So
Yeah.
it can go up to more.
It can do whichever. Some cases, and we
really don't know.
right, we what we can show, it comes down to quantum effects, okay? So it's hard to kind of just explain away without understanding quantum physics a little bit. But if we fire a single electron, we'll see, okay, we'll shoot one electron. We'll see what this one does. So it goes to 3, and there it went right back to 1. And it just gave off one purple photon because there was one jump. No. It's only red if it goes from 3 to 2. Let's fire another one, and we'll see if it'll do the double jump. So there it goes from 3 to 2 to 1. So here we see the purple light. That was just like when we were only getting it up to 2. And then the red light is the one when it goes from 3 to 2. Okay? So let's fire another one. So the number of photons corresponds to how many jumps there are. See, there it only jumped from 3 to 1. So you get one photon, high energy. Right. And big energy jumps mean light that's towards the purple end if we're talking about visible light, or it could be UV or gamma, whatever. High energy. Okay. Yes. Now we're going to crank up the volts even more so that here it can jump all the way. They've got 6 energy levels. Okay. So there's multiple things that could happen. When it gets kicked up to 6, it could fall all the way back down, and you would get one photon, one light wave. If it goes from 6 to 3 to 1, you would get 2. If it goes from 6 to 5 to 3 to 1, you would get 3. And so there's, depending on what's going on, there could be all different types of wavelengths that are going out. So we're going to reset our spectrometer here. We're going to shoot an electron, and we'll see what happens. So it went from 4 to 1, so we see 2 photons that were produced. Okay, we'll shoot another one. So 6 all the way to 1, just 1. Braden. 3 to 2 to 1. Okay. What would be cool is if we could see all the energy jumps. 6 to 5 to 4 to 3 to 2 to 1. But it's all random, so just like flipping a dice, you don't know what's going to happen. So that was. Yeah, so the 6 to 4 produced the kind of the light blue color, and then the 4 to 1 produced the purple. Yeah, we will in a minute.
Mr. Roark, I have a photon gun.
You do?
I got it on the dark web.
Okay. There's another 6 to 1.
Yeah, several. One pair, and then one like normal one.
That one only went to 5 for some reason.
Who's Asian?
2 to 1.
We really like
2 to 1.
all the way down.
Yeah. All right, let's start on continuous.
Yeah. Oh, yeah. Oh, yeah. Oh, yeah. Oh, baby. This is just fast. What was that? That was a brighter purple. Yeah, that's a crazy purple.
So, I mean, the bigger the jump, the more towards the purple end it'll be. So if you get a 6-to-1, that'll be really purple. If it's only a 5-to-1, it'll be a little bit different. And what this does is it charts. Well, here's the thing. For it to be red, it has to be one of those small jumps there. And so you're always going to get more purple because it's always got to fall down to 1. There'll be a few.
There's a red, darker red. This is really dark.
Okay. Now remember, when we looked at the emission spectrum for hydrogen, there's different lines, right? This is what we're showing right here. This is hydrogen. And so by shooting these electrons through the air, because there's all these different jumps that the electrons can do, we get these different lines that are being produced. And so if we let this go long enough, I don't know why it's moving so slow, we'll see all of those lines being produced. It'll be brighter at this end because there's more photons that are being produced with those wavelengths because there's more, it's more likely it's going to make those jumps. But we'll see some of these other colors as well. Okay. Now this down here corresponds to infrared. That's low energy. Which jump is most likely going to be infrared? Nope. 6 to 5, because 6 to 5 is going to be the smallest energy jump. The energy levels get closer together as you get further up. Yeah, remember the stairs? The stairs got closer together that we drew up yesterday.
There's a bright red.
Does it only go up to 6 or what?
In this simulation, hydrogen only goes up to 6. Yes. No. Uh-huh. You mean like right here? As you follow this up, it isn't just like a solid line. They're just kind of recreating how it tends to look like in a spectrometer, and that comes from some waves interfering with each other. It's kind of an artifact. We call it an artifact because it's there, but it doesn't really matter. Okay. Any questions about this before we move on to something else? Because there's more stuff we can do here.
Go to maximum power. I still don't understand the red thing. Graph, the chart thing.
This thing?
Yeah.
So this is charting basically how many light waves are produced of that color. Okay? So we're getting lots of UV, some purple, or a bunch of purple, a few of these, a few of these, a few of these, and it just corresponds, those colors correspond to what energy level jumps there are. Okay? These are like the 6 to 5, or maybe the 5 to 4. This one. Okay? This is going to be more like the 6 to 3. Okay? As you go more towards the purple, those are bigger jumps because they have more, they're associated with more energy. The bigger the jump, the more energy, the more towards the blue side of the, and we say the blue side, but really what we mean is more towards like the gamma rays and X-rays. Okay? The more, or the less energy they have, the more it's going to be towards like radio waves and microwaves. This is just showing visible light. Yes, Brayton, I have a microwave. All right, let's stop this here. Now let's change to sodium. Okay? What's that? Right, but look at the energy levels here. They're closer together. So are we going to expect to see any UV produced here? Probably not. There's not enough, gaps in between there. So here we would expect to see more colors down towards this end of the spectrum, the lower energy. So let's crank this one up and see what happens. Now, there's different colors produced here because of the different energy level gaps. They're not the same as they are in hydrogen, so we expect to see different colors. Why does it not look like my spectrometer is working? Aw, man. Okay, let's chart this first, and then we'll investigate that. What would happen if we lower the voltage? What do you think would happen if we lower the voltage? It wouldn't go up as high, so there'd be less colors produced, right? We would not expect to see some of these colors on there because it's not going all the way up to 6. There's not as many energy level gaps that it can jump around. What's that? Sort of.
I got a concussion and it's stimulating.
I mean, you were still here, so
Oh!
there was still some distraction. That's true.
What happens when you try to roast other people? Yeah, but I like singing.
Okay, so here we see, a bunch of colors produced. They're different than the hydrogen ones. They're lower energy. We don't see really any blue or UV because there just aren't those big of gaps in the energy levels. Sodium lights are actually used all the time for street lamps. So those, the street lamps that kind of give a real, yellowish color off, okay? Those are, sometimes they're sulfur, but mostly they're sodium gas lamps. And it works exactly like this. They have sodium in a tube, and they send electricity through it. And what we see is mostly, there's going to be some heat given off too, but it's mostly going to be yellowish and orangish light that's given off, and that's why they kind of have that color. But they're fairly energy efficient, so that's why they use them. Oh, LEDs are completely different on how they produce light. They're very complicated. You have to understand quantum physics to be able to get it. Light emitting diode. So, quantum physics.
How do we know that's not all just fake?
Well, that's a good question. How do we know that this isn't all fake?
Yeah, exactly. That's what I asked earlier.
Because when somebody came up with this idea, this is how it works, right? That these electrons are jumping around, then people go, okay, well, if that's true, then it would mean this, and that's a testable thing. And they go and they test it, and they go, oh, that does happen. Oh, that gives some credibility to, the explanation. And there's lots of different things that we can test, and as long as those all line up and they seem to make sense, then it gives more credibility. The thing about science is there's absolutely nothing where we know for sure 100% without a doubt. It's always everything points to this. There's no reason to think that it's not. That's the world that we live in. That's the way science works. That's no reason to distrust stuff. Yes, it is possible that there's some weird physics that we haven't discovered that explains gravity, but we're pretty sure we know how gravity works. And that's the same with a lot of things. Evolution's the same.
The British were also pretty sure they won the Revolutionary War.
Let's look at neon.
And they didn't.
Okay, so here's neon. Okay. Let's do this. Let's reset this. Stop this. Why? Right. This energy gap from here to here is so big, we need a lot of energy to jump it to that higher energy level. So we need to crank up the electricity here.
What's the point of this? You can't get it that high.
A 12-volt battery in there.
So what this is showing is with a single atom, you can actually make neon give off light. Okay? So let's change over here and go to multiple atoms. Oh. So we can do the same thing. We're going to stop this, though. Let's go to single. Just a minute. You guys are always asking the questions that I'm just about to try to explain. Okay, let's fire a single electron out of here and see what happens. So this is neon. We got it cranked all the way up. Okay. Now here it's not showing what the energy is, but think about when we look back. We don't have enough. We know we don't have enough energy to kick it all the way up to this energy level, right? Okay. Let's see what happens when we fire an electron. That one's not going to hit anything. There we go. Okay. Photons of light can be absorbed by electrons to kick them up to higher energy levels too. What? Okay. I don't know. She looked right at me and did some weird thing with her neck, so. I was confused. Anyway, the point is, when you have a group of atoms, the light that's given off can actually hit another atom and cause the electron to jump up there. And so in that case, we can actually get multiple things going on in an atom to kick them to those higher energy levels. Right, like pinball. So let's set the continuous and jump it up. And now we can see we do have enough energy to hit up because some of these are getting kicked to a higher energy level. Well, listen, they're getting kicked to a higher energy level, and before they fall back down, another photon hits them and kicks them to an even higher energy level. Okay? And so because of that, we can actually get things to a higher energy level with multiple atoms than we would be able to by ourselves. It's sort of like, let's say we had a mountain, and Isaac tried to throw a baseball up the mountain. Obviously, he can't throw that high. Okay? Shh, listen. But if we all stood at multiple spots up the mountain and we threw it to each other, we could get that baseball up the mountain. So that's what's going on here. When one electron gets kicked to a higher energy level, another light can come along and can get absorbed and kick it to an even higher energy level. We get all this different light that comes out that's being produced because of all those interactions of the electrons falling down. Let's turn on our spectrometer here and measure the light that comes out. Oh, yes, we can turn the squiggles on for you, Hunter. There we go. Woo. Okay, you can see there's a fair amount of UV given off because, of course, there's a big energy gap from here to here. I mean, I don't know if you guys can see, but this is a 5. There's like 5, 4, 3, 2, all kind of really close together here. So there's small energy gaps between those, but to go from 2 all the way down to 1, there's a big energy gap. So there's going to be a lot of UV. Right. No. The energy but Isaac is absolutely right. The energy level gaps are different for different elements. By doing absolutely this, by putting the elements in a tube, sending electricity through, and measuring the light that comes off. Because we know each of these wavelengths of light corresponds to a different gap. And that's why we can fingerprint these different elements by their emission spectrum. Everyone is different because they have different energy gaps. Okay? So that's kind of cool. And then, let's see. Let's shut this off. Well, this is kind of what we're doing. There's mercury, too, so we can look at the energy level gaps there. Okay? But what's cool is you can go to a configurable one. So here, you can actually change where you want that energy level to be. So, let's go. Okay, let's go way down here. We're just gonna do 2 levels for now so that we can kind of see. Just a minute. So what type of light should be given off here?
Ooh, red.
Towards the red end. Oh, we got to turn our spectrometer on.
Oh, can't forget that. Oh, geez.
Okay. Now, this energy level gap is so small, it's not even like red, it's in the infrared, right? So how would we make it actual red?
Put it all the way down.
Move the energy level.
We need to move that energy level up a little bit.
Squiggles just follow the line.
There you go.
Oh.
There, we're getting some red, some orange. I went a little too far. We're in the orange. Okay. If I move it up, what's going to come after orange? Yellow. Think about your rainbow, right? So then we go through green. Blue is higher energy, so there's blue. This would be, I guess, indigo. I don't know. Indigo is not really a color. Isaac Newton just threw it in there because he thought things should be on things with that are centered around the number 7 are important in a lot of Christian tradition. And so he thought that there should be 7 different colors. So when he looked at the rainbow, he's like, oh, yeah, there's a color in between blue and purple. Let's call it indigo. But then we go up higher, and it gets more purple, and then into black, but UV. Okay? And here you can actually put all sorts of different energy levels. Oh, it only lets you go to 6, but and you can play with those. So you can figure out what types of light are given off based on all those different gaps.
Let's get that whole thing solid color.
You'd have to move those around and let it run, and I don't want to do that. Yes, it is. So this actually shows real discharge lamps, but this is what we saw yesterday with the gas tubes that I had up here. So we saw hydrogen, it looked just like that, right? We saw neon, it looked just like that. We saw the mercury. I don't have sodium, but sodium is this yellowish color like that. So remember, real neon lights are red. If they're any other color, there's some other gas that's in there. Yes. Well, it's one of those things, it's like Tylenol, right? There's a lot of different companies that make acetaminophen. That is the thing that we take. Tylenol is just the name of one of those, but everybody calls acetaminophen Tylenol just because that name stuck. Same with Kleenexes. And Frisbees. And jet skis.
It's actually called personal watercraft.
Yep.
You know Dominic goes to ski. Oh no! I'm sure you got a concussion. You should have warned him. I'm not going by. You're gonna cry. All right. You're gonna rub your back on this. Thank you.
Okay, any questions about light and energy levels?
No.
Did that help a little bit, looking at that?
Yeah, it makes
It's
sense.
just random. That's all we gotta know.
Yeah,
You know a little bit more than that, but
every bigger the jump, the more energy it's going to have.
Well, yeah.
The less energy, right? Or the more?
the bigger the jump, the more energy the light's going to have. And the more energy it takes to get it there. Remember,
So which color has the most energy? Purple?
yeah.
Okay.
Gamma has the most, X-rays, UV, purple light,
More energy.
all the way down.
More energy to get out.
But remember, you have to have enough energy to kick it to that next energy level too. If there's not enough energy in there to knock the electron up, just like that when we had a single neon there, then nothing's going to happen.
The highest visible light.
Right. Purple is the highest energy visible light.
That's right, Isaac.
Good job, Isaac.
Starting to catch on, Roark. I know that.
Yeah, the other thing that I think it would be good to talk about and review a little bit, because I think there's some confusion, is the fact that we have two equations.
The light equation, which is God dang it, some one times move your freaking chair.
We have to be able to use each of these equations when they are needed. So the first equation, remember, relates the frequency and the wavelength of a light wave, and it's all based around the speed of light. Talking about this equation right here. Okay? So remember, c is the speed of light. It is just a number, and it's a constant. If you look on your equation sheets, I don't expect you to memorize. I mean, you might remember it, but I don't expect you to memorize constants. So it is listed on your sheet, c equals 3 times 10 to the 8th meters per second. Great. But I'm saying on the constant sheet, 3 times 10 to the 8th meters per second. Yes. But that's what we use.
What kind of vacuum? Like a Dyson?
3.00. It's actually 2.998 something, but since we rounded 3 sig figs, we can just go with 3.00. Okay? The other equation, right here, basically lets us calculate how much actual energy a light wave has based on its frequency. And in this case, we use a different constant called Planck's constant. That also is on your equation sheet.
So which variable is constant?
H. Okay? And guys, if you look at your equation sheet right here, okay, here's C, 3 times 10 to the 8th meters per second. Here's H, 6.62 times 10 to the negative 34th joules times seconds. Yes. It's my favorite thing when I say something and then half a minute later you ask the same question that I just answered.
You don't have to do anything for J10 test again.
What does upside down Y have to do?
Okay, I'm going to go through each of these, okay?
Yeah, what does that have to do?
Listen.
Wavelength.
So, this right here, the whole point of this equation is to let us go, hey, I know the frequency of a wave, I wonder what its wavelength is, or I know what the wavelength of it is, I wonder what its frequency is. That's the whole point of this equation. Basically just to switch back and forth between frequency and wavelength. Now I know you can look at this chart and sort of get an idea of that, this chart right here, right? But this is, this is very general, right? I can go, oh, this is about this, it must be about this. This frequency is about this, it must be about this wavelength. We want to actually calculate it though. What?
Does it have to be in nanometers in this formula or meters?
Meters. That's important. Okay? Because the speed of light is in meters per second, okay, for this equation to work, the wavelength has to be in meters and the frequency has to be in hertz, which if you remember, hertz basically means a wave per second. So that's where the seconds come from. Okay? So let's do a typical problem that you might see using this equation. Let's say you have a wave with a wavelength of 6.89 times 10 to the negative third meters. We want to be able to calculate its frequency. Okay, now these are just 3-part equations. We know this has to be this number. We can even put that into our calculator and store it as C. This is our wavelength. We have to divide on each side by the wavelength, so we're basically going to take the speed of light and divide it by the wavelength to find the frequency. What? Good. Good choice.
I feel like we're just going to blow up on these things. Go off.
Well, he has a hydrogen bomb. Yeah, you got it to start looking.
I don't know where my calculator went.
Hunter has it.
I don't have my calculator.
No, not that one. My good one.
Oh, your good one?
I don't have that one yet.
My good gray one.
I bet Hunter stole it.
No, I have this one.
Oh, there it is.
I have a
So in this case, you should get a frequency of 4.35 times 10 to the 10th hertz. Okay? Does everybody feel comfortable with that? Now the only difference is you could be asked the other way around. I might ask you, hey, I've got a frequency of this, what would the wavelength be? But because of the way the equation is set up, it doesn't really matter which one you're looking for. You always take the speed of light and divide it by the one that you know to find the one that you're looking for. Okay? Now, here's the point of this equation. The point of this equation is to go, hey, we know this wave has a frequency of 4.35 times 10 to the 10th. How much energy is it carrying? How much, and this is going to be related to the electrons, because it's the same answer if we ask the question, how much energy does it take to get an electron to this energy level? How much energy is going to be given off if the electron jumps from that energy level down? Because all of those energies have to be equal. If it takes, I'm just going to make up numbers here, if it takes 5 million joules to jump an electron, that's way too high, but to jump an electron from the first energy level to the second energy level, then when it falls back down, it's going to give off 5 million joules, and the light that it carries is going to be 5 million joules. All of those things have to be equal. Well, that would just be finding the whether it's UV or whatever. Okay. So in this case right here, we take the frequency and we multiply it by Planck's constant to find the energy. And again, Planck's constant is just a number. It's just 6.62. I get this mixed up with a different constant in physics all the time. 6.62 times 10 to the negative 23rd, right? Joules times seconds. Oh, 34th, that's right. This is why you should look it up instead of trusting your memory. It doesn't make that much of a difference if it's 6.2 or 6.3, really. I guess I've got 6.2 on here. That'll all come out in the wash. Okay, so all we really have to do is multiply this, which is a constant. It never changes. In every single equation you do, this will be the number for H. And you multiply it by the frequency and find the energy.
How do we put that into our calculator?
This is just the units that go along with it. It's just the units.
Take my last number
Okay.
times this one.
Yep.
How do we enter it in as like a letter?
Hit the store. I don't know. I've explained that like 8 times. So you were here other days when I explained it.
Yeah, but I don't remember it. I got both in the phone. No, you don't.
Okay? The thing to remember is energy is measured in joules. Okay? And really when you do the math, the hertz is 1 per second. Okay? It's 1 wave per second. So when you multiply 1 wave per second times joules times seconds, the seconds cancel out, and that's how you get joules.
So would there be time seconds instead of the units?
The seconds is...
They're always going to cancel out?
Yeah, the seconds are part of this, part of the hertz, because the hertz means 1 per second. Okay? I mean, we could also put up here joules per hertz. It's just we always see it in joules times seconds. It's just a label. Now, here's the thing. We also have to be able to think a little bit more, globally, because another question I could ask is, hey, this wave has a wavelength of this much. How much energy does it carry? And a lot of times students go, well, there's no equation up there that has both energy and wavelength in it. But what could you do? No, not dimensional analysis.
So how did you do that? I just type in the numbers and press those?
Anybody? If I asked the question, here, let's do it. We got just enough time. Let me put this down.
Yeah, don't worry about it.
So, if I ask the question, how much energy is carried by a wave that has a wavelength of 9.87 times 10 to the negative 12 meters? What would you do? You use the first equation to find the frequency, and then use the second equation to find the energy. Okay? So sometimes you might have to use two equations for one problem.
That's stupid.
Okay? In reverse, I could also say, listen, I could also say the energy gap between two energy levels in an atom is this many joules. What will be the wavelength of light that's given off if an electron falls from that energy level? And so first you use the energy to find the frequency, and then you use the frequency to find the wavelength. You're using both equations. Okay? So these are constants. These are all measurements, but we should be able to go back and forth between all three of them. So if I ask the energy and I want to find the wavelength, there is no equation that directly relates those. First I have to calculate the frequency using this equation, and then you stick the frequency into this equation to find the wavelength. We will be practicing that tomorrow. Yes, tomorrow. Actually, I should say you guys will be practicing that tomorrow. No, you're not going to be gone. I will be gone.
Well, depending on.
So how are you doing the gender today? You gonna dunk it?
I thought you were a big basketball player back in the day.
You have a good sky look? Yeah, yesterday we didn't have time.
I know you didn't have time because you guys kept stalling.
You should have seen my guest yesterday at Polaris on corner of 10th. So you're saying...
Let's see. There we go. Here we go. Let's do a molar mass problem. It's been a while.
Oh my God! Jesus, Roark. Okay, I got this. Remember now, I mean,